All right, we're in MAT 221. This is Calculus 1. This is Mrs. Johnson. We're in section 2.6, talking about the derivative at a point. This is video number 3. Here's another example that we're going to look at. It says in figure 2.23, for each of the following pairs of numbers, use figure 2.23 to decide which is larger, and then explain your answer. All right, so first, let's look at A. It says, which is larger, f of 3 or f of 4? Well, what are those actually? F of 4 is the value of the function at 4. F of 3 is the value of the function at 3. Which one's larger? F of 4 is larger, obviously. It has the higher output value. What about part B? Which is larger? F of 3 minus f of 2 or f of 2 minus f of 1? Now, what are those values actually? F of 3 is that y value. F of 2 is that y value. So the difference between the y values, or this little piece right here, would be f of 3 minus f of 2. So if we took f of 3 and we subtracted f of 2, we would get that little piece right there. Now, what about f of 1 and f of 2? Here's f of 2, here's f of 1. We would get this piece right here, the difference between the y values, right? These are the output values. So it would be the difference between the y values. Which one's bigger? Obviously, that second one was bigger. Part C asks us for f of 2 minus f of 1 over 2 minus 1. Wait a minute, that's simply slope between 2 points. So this is between f of 2 and f of 1. That's the slope between those 2 points. Or f of 3 minus f of 1 over 3 minus 1. That is slope. That is the slope between f of 3 and f of 1. Which two of those slopes is bigger or steeper? The first one is a steeper slope, a more positive slope. Last question, which one's bigger, f prime at 1 or f prime at 4? What does that mean? That means the derivative of the curve or the slope of the curve at one point, or the tangent line to the curve, slope of the tangent line to the curve. Here's f of 1, here's f of 4. This would be the tangent line to the curve at 1. This would be the tangent line to the curve at 4. Which one is steeper? Which one is bigger? Which has a greater positive value? F prime at 1 does. It has a steeper slope here than here. Next, we're going to look algebraically of functions. We're going to find the derivative at a point. We want to find what is the derivative of 5x squared when x equals 10. Now, I'm going to do the derivative at a point, so I'm going to put into that formula that we have f of a plus h minus f of a over h. But in this case, I'm putting in 10 in for a because that's the value where we want the point of tangency. That's the point where we want the derivative. So I'm putting into the formula where that value is in this case. Now, what would f of 10 plus h be? Well, we're going to take 10 plus h and put it into the function that we're talking about here, which is 5x squared. So that would be 5a plus h, or in this case, 10 plus h squared. That's f of 10 plus h, minus f of 10, which would be 5 times 10 squared, all over h. And we're going to take the limit as h approaches 0. Foiling this part out, I would get 100 plus 20h plus h squared. And then I'm going to multiply that by 5, so I would get 500 plus 20 times 5 is 100h plus 5h squared minus 5 times 100, which is 500. So here's, at this point, is just algebra. We're not actually doing any calculus here. The only calculus is actually the formula, and then when we take the limit. Those 500s are going to cancel, so we're going to get 100h plus 5h squared all over h. We're going to take the limit as h approaches 0. I can't do a limit by substitution yet because I still have an h in the denominator, which is going to give me a 0 denominator. So I'm going to factor out an h out of the numerator and then cancel those h's. So this h would cancel with this h, so I'd get the limit of 100 plus 5h. Now I can do a limit by substitution and put in 0 in for h. My derivative when x equals 10 is equal to 100. That is the derivative of this curve at x equals 10. It is the slope of the tangent line to the curve at x equals 10. It is the slope of the curve at x equals 10. It is the instantaneous rate of change of the curve when x equals 10. Let's try another general derivative where we don't use an actual number, but we actually put a letter in here. So we're going to actually use a in here for x. We're still going to use the same formula that we've always done here for the derivative at a point. We're going to say, what is the derivative at a? I'm going to put in f of a plus h minus f of a over h. Now again, this is function notation that we learned in earlier courses. So function notation says wherever I see x, I'm going to replace it by a plus h. And in this case, wherever I see x, I'm going to replace it by a. When I do the algebra here, I'm going to put in a plus h into the general formula here. So I get a plus h squared, which came from this formula here. I put a plus h for x, and I got this. I put a plus h for x, and I've got this. And then I have a 9. So this whole expression is f of a plus h minus f of a. So I'm going to put a in for x, and I get this. Be careful to put a parentheses because of the subtraction, because remember we distribute around that subtraction. And then the denominator is just h. All right, we're going to do a lot of algebra here. Foiling out this first term, we get a squared plus 2ah plus h squared. Distributing the negative 8, I get negative 8h minus negative 8a minus negative 8h plus 9. Distributing the negative here, I get negative a squared plus 8a minus 9. Let's combine some terms here. The a squareds will cancel each other out. The 8a and negative 8a will cancel each other out. The 9 and the negative 9 will cancel each other out. And I'll get the limit as h approaches 0 of, I'm going to factor out an h out of the numerator. So if I take out this h and one of these h's and that h, I get h a factor of 2a plus h minus 8 over h. Canceling out the h's, now I can do a limit by substitution because now the h's are gone in the denominator, so I can simply substitute 0 in for h. This gives me my general derivative for this curve when x equals any number a. So now I could figure out the derivative of the curve at any point on the curve by simply substituting that x value in for a. This is called the general derivative at a point. All right, that does it for section 2.6. Go back and now go into your web assigns for section 2.6 and do that work. Have a great day.